In this lesson, we will examine some techniques for solving equations involving fractions. Let's begin with this question. To solve this equation, we will use the fact that when we multiply a fraction by its reciprocal, the product is 1. So if we take our equation here and multiply the left-hand side by 5 over 2, we have 5 over 2 times 2 over 5, which equals 1. So the product here is 1x, or just x. Now if we multiply the left-hand side by 5 over 2, we must also multiply the right-hand side by 5 over 2. When we multiply 8 by 5 over 2, we get 20, so the solution here is x equals 20. Now please note that we can express fractional coefficients in more than one way. For example, writing 2x over 5 is the same as writing 2/5 times x. Okay, let's try another one. Here the coefficient of x is 3/4, so we'll multiply both sides of the equation by the reciprocal, 4/3. Now on the left-hand side, the fractions cancel out, leaving us with x. And on the right-hand side, 1/7 times 4/3 is equal to 4 over 21. So the solution here is x equals 4 over 21. Okay, now let's examine a more advanced question. Our goal here should be to eliminate our fractions first. We can do this by multiplying both sides of the equation by the least common multiple of the denominators. So in this equation, the denominators are 4, 2, and 3. Since the least common multiple of 4, 2, and 3 is 12, we will multiply both sides by 12. Now I will write 12 as 12 over 1, so you can see that we are multiplying fractions here. Now at this point, we need to expand the left-hand side. So first we will multiply 12 and 3x over 4 to get 36x over 4. Next we'll multiply 12 and 1/2 to get 12 over 2. Now I could have simplified these products, but I'll do that in the next step. On the right-hand side, we'll multiply 12 and x over 3 to get 12x over 3. At this point, all of our fractions simplify nicely. 36 over 4 is equal to 9x, 12 over 2 is equal to 6, and 12x over 3 is equal to 4x. Now that we have eliminated the fractions, we have a relatively simple equation to solve. From here, let's subtract 9x from both sides. And now we'll divide both sides by -5 to get x equals 6 over -5, which we can also write as x equals -6/5. Okay, here's another example. Once again, to eliminate the fractions, we'll multiply both sides of the equation by the least common multiple of the denominators. Here, the least common multiple of 10, 5, and 12 is 60, so we will multiply both sides by 60. From here, we will expand both sides beginning with the left-hand side. 60 times x over 10 is equal to 60x over 10, and 60 times 4/5 is equal to 240 over 5. On the right-hand side, we'll multiply 60 by x over 12 to get 60x over 12, and we'll multiply 60 by 1 to get 60 over 1. At this point, all of our fractions simplify nicely. 60x over 10 equals 6x, 240 over 5 equals 48, 60x over 12 equals 5x, and 60 over 1 equals 60. From here, we can solve for x by first subtracting 5x from both sides. And now we'll subtract 48 from both sides to get x equals 12. Now here's a more advanced question. To eliminate the fractions here, we'll multiply both sides of the equation by the least common multiple of the denominators. The least common multiple of 2 and 3 is 6, so we will multiply both sides by 6. Now let's expand the left-hand side. 6 over 1 times the first rational expression is equal to the following, and 6 over 1 times the second rational expression is equal to this. On the right-hand side, 6 over 1 times x is equal to 6x over 1. At this point, notice that 6 over 2 here can be simplified to be 3, and 6 over 3 can be simplified to be 2. Finally, the right-hand side simplifies to be 6x. Okay, we have now eliminated our fractions. Now we need to do some expanding. First, 3 times 3x is 9x, and 3 times positive 2 is positive 6 or plus 6. Next we have negative 2 times x, which is negative 2x or minus 2x, and we have negative 2 times positive 1, which is negative or minus 2. This is all equal to 6x. At this point, we can simplify the left-hand side to be 7x plus 4, and now we can solve for x by first subtracting 7x from both sides, and then dividing both sides by negative 1 to get x equals negative 4. Okay, let's examine one last question. For this question, it seems difficult to use the technique of multiplying both sides of the equation by the least common multiple of the denominators, since it's hard to tell what is the least common multiple of 6x minus 6 and 2x plus 2. Now, whenever we have two rational expressions set equal to each other, we can use the following extension of the least common multiple rule. It says, if a over b is equal to c over d, then it must be true that a times d is equal to b times c. In this equation, there are two equivalent rational expressions, so we can apply this rule and conclude that 7 times 2x plus 2 must equal 3 times 6x minus 6. At this point, we have a nice equation that we can solve for x. First, we'll expand the left-hand side, and then we'll expand the right-hand side. Then we can subtract 14x from both sides, and now we can add 18 to both sides. Finally, when we divide both sides by 4, we get the solution x equals 8. Okay, let's summarize. Some basic equations can be solved by using the fact that the product of a fraction and its reciprocal equals 1. Also, we can eliminate fractions by multiplying both sides of an equation by the least common multiple of the denominators. And finally, if we have two rational expressions set equal to each other, we can cross-multiply and then solve the resulting equation. In this lesson, we will examine some techniques for solving quadratic equations. To begin, a quadratic equation is any equation that can be written in the form ax squared plus bx plus c equals 0, where a does not equal 0. So here are some examples of quadratic equations. Notice that we could take these equations and write them in the form ax squared plus bx plus c equals 0. Another way to look at it is to say that a quadratic equation is an equation that has one variable raised to the power of 2. Now, when it comes to solving quadratic equations, like the one shown here, the techniques we have learned so far will not help us. For example, we might try to solve this question by first subtracting 23 from both sides of the equation. But then what do? If we add 9x to both sides, the equation appears even more problematic. So it appears that we need a new technique for solving quadratic equations. To introduce this new technique, I'll pose the following question. If a and b are numbers, and we are told that a times b equals 12, what conclusions can we make about the values of a and b? Well, if a times b equals 12, then it could be the case that a equals 2 and b equals 6. Or it could be the case that a equals 12 and b equals 1. Or a could equal negative 3 and b could equal negative 4. As you might guess, the number of possibilities is infinite. However, notice what happens if we change the question slightly. If we are told that a times b equals 0, what conclusions can we then make about the values of a and b? Well, if a times b equals 0, then it must be the case that a equals 0, b equals 0, or they both equal 0. Now, this is a very powerful conclusion. When the product of two numbers is 0, we know a lot about these numbers. So how can we use this to solve our quadratic equation here? Well, to begin, if we first subtract 3 from both sides of this equation, we get a new equation set equal to 0. and we happen to know that if the product of two values is equal to 0, we know a lot about those values. But how does that help us if we don't have a product here? Well, in an earlier lesson, we learned how to factor these types of quadratic polynomials. This particular expression can be factored to be x minus 4 times x minus 5. Notice that we now have something times something equals 0. So according to our new rule, either the first something equals 0, or the second something equals 0. Now if x minus 4 equals 0, then x must equal 4, and if x minus 5 equals 0, then x must equal 5. So there are two possible solutions to this equation. X must equal 4 or 5. You will find that most quadratic equations will have two possible solutions. Alright, let's solve another one. This equation is already set equal to 0, so we can apply our rule if we are able to factor the left-hand side here. When we factor the left-hand side, we get x plus 6 times x minus 4 equals 0. Now that the equation is in the form something times something equals 0, it must be the case that the first something equals 0, or the second something equals 0. If x plus 6 equals 0, then x must equal negative 6. And if x minus 4 equals 0, then x must equal 4. So the two solutions to this equation are x equals negative 6 and 4. This next equation is a little harder. Notice that the left-hand side here is one of those special products in this form. As such, we can factor it to be 3x plus 1 times 3x plus 1. Now that the equation is in the form something times something equals 0, it must be the case that the first something equals 0, or the second something equals 0. If 3x plus 1 equals 0, we can solve for x by first subtracting 1 from both sides, and then dividing both sides by 3 to get x equals negative 1/3. Since the second equation is identical to the first equation, it will yield the same result. So for this quadratic equation, there is only one unique solution, that is, x equals negative 1/3. Now you will find that the vast majority of quadratic equations found on the GRE can be factored using the same approach we used for the last three questions. However, if you do come across a quadratic equation that you cannot factor, you can always use the quadratic formula to help you solve it. The quadratic formula says that if you have a quadratic equation in the form ax squared plus bx plus c equals 0, then the solutions to that equation will be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I'll explain the plus or minus part in a second. Let's use the quadratic formula to solve this equation. In this example, we can see that a equals 10, b equals 3, and c is equal to negative 4. We'll now take these values and plug them into the formula. From here we can simplify the part inside the square root to get 169. And the square root of 169 is 13. So we now have x equals negative 3 plus or minus 13 all over 20. This means that one of our solutions is x equals negative 3 plus 13 over 20, and the other solution is x equals negative 3 minus 13 over 20. Let's simplify the first one. Negative 3 plus 13 is 10, so we have 10 over 20, which is equal to 1/2. For the second solution, we have negative 3 minus 13, which equals negative 16, and negative 16 over 20 can be simplified as negative 4/5. So the two solutions to this equation are x equals 1/2 and x equals negative 4/5. Now, as I said, it is very unlikely that you will ever need to apply the quadratic formula to a GRE question. However, it is conceivable that there are some advanced questions out there that might require you to know a little bit about this portion of the formula inside the square root. The question might require you to be aware of the fact that some quadratic equations cannot be solved. they have no solutions. This occurs when we get a negative value inside the square root sign here. Since we cannot find the square root of a negative number, it must be the case that a quadratic equation will be impossible to solve if we end up with a negative number inside the square root. So if we have a quadratic equation in the form ax squared plus bx plus c equals 0, such that b squared minus 4ac is negative, then that quadratic equation will have no solution. If b squared minus 4ac is greater than or equal to 0, then that quadratic equation will have a solution. Okay, let's summarize. In this lesson, we learned that equations that can be written in this form are called quadratic equations. Most, if not all, quadratic equations you will encounter on the GRE can be solved by factoring. If a quadratic equation is solvable, it will have either one or two solutions. You can use the quadratic formula for solving quadratic equations that are difficult to factor, and there are certain conditions under which quadratic equations do not have solutions.